Okay, so let us first consider the region in the xy plane bounded by the following two curves. So we'll take first y equals negative x squared plus 2. Second, y equals negative x plus 2. So we have an inverted parabola and a line of negative slope. Let us first find the points of intersection. So we equate both y values. Sum everything here on the left, so add x, subtract 2. You'll get negative x squared plus x equals 0. You can factor in negative x. And now the solution should be apparent. Either x is 0 or x is 1. If x is 0, y is 2. And if x is 1, 2 minus 1 is 1, so y is also 1. And so we have our points of intersection, 0, 2, 1, 1. And now we can sketch the region bounded by these two curves, knowing the points of intersection. The inverted quadratic, and our line. Again, a line of negative slope, and an inverted quadratic. So this is the line y equals, as we have said, negative x plus 2. And this is the quadratic y equals negative x squared plus 2. And the points of intersection, of course, are x equals 0, y equals 2. So at this point right here, the y value is 2. And this is the other point of intersection, x equals 1, y equals 1. So the x value here is 1, and the y value is also 1. Okay, so we can clearly see now the region bounded by these two curves. And once again, we will think of this region in the xy plane being the base of our solid. And with this base, how do we construct a solid? Well, we will choose to erect semicircles that are 1, perpendicular to the base, the region in the xy plane, and 2, perpendicular now to the y-axis. So imagine taking a little cross-section of the region of the solid that is perpendicular to the y-axis. It is positioned along the y-axis. And so we're slicing through our solid this way, and as we've said, we are erecting semicircles on top of our region that are perpendicular to the region, so they're standing straight up about the base, and they're also perpendicular to the y-axis. So let me draw a little semicircle cross region, and those again are infinitesimal cross sections. I'll try and magnify it. So here's your little cross section. So again, imagine that this is the base, the region is the base of your solid, and onto this infinitesimal rectangle, you pick up, right, the base of your semicircle is this little rectangle, so you pick up this infinitesimal semicircle and you place it onto this rectangle in a perpendicular fashion with respect to the base of your region, the base of your solid. So you pick this little semicircle and you place it right on top of your region. And as you place all of these infinitesimal semicircles everywhere onto the region, it will generate a solid. And we're going to ask, what is the volume of this solid? Well, let us first find the volume of an infinitesimal semicircle. If you think of it, what is the thickness of your semicircle? Well, it is the width of the rectangle. The width is an infinitesimal change along the y-axis, so of course given by dy. To find the area of a semicircle, we need the radius. So this will be the radius. But if you notice, the radius is half the length of the rectangle. So if we can find the length of our rectangular base, half of it will be the radius. So let's find the length of our rectangle. Well, the length is a segment along the x-axis, so we need the larger x value and the smaller x value. So let me call this x1, let me call this x2. And again, because we have a dy, everything we measure must be a function of y. Well, let's solve for x1 first as a function of y. We are on this line, and if we solve for x, send x over here, you'll have that x plus y is 2, subtract y, and so x will be 2 minus y. So x1, the value of x here, is 2 minus y, the smaller x value. Now we need the larger x value, x2. This one's a bit more interesting. If you think here we are on this curve, the quadratic, where y is negative x squared plus 2. Now we want to solve for x as a function of y. So send x squared on this side, and you get x squared plus y equals 2. Subtract y, so x squared equals 2 minus y, and now there are two solutions. X is either plus or minus the square root of 2 minus y. And which one do we take? Do we take the square root of 2 minus y or the negative of the square root of 2 minus y? Well, look at our region. Our region lies in the first quadrant of the xy plane, where the x values are non-negative. So we must take the positive of the square root of 2 minus y. And so, in the first quadrant on this curve, x is the root of 2 minus y, as this is the positive solution. And that is our x2. And now we can of course find the radius. The radius is the length of the rectangle over 2. So we take the bigger x value, root of 2 minus y, minus the smaller x value, 2 minus y, and we divide by 2. Okay. So now we have our measurements. So if you think of it, the volume of our infinitesimal semicircle is given by the area of the semicircle times the thickness of our semicircle. Well, the area of a circle of radius r would be pi r squared. But we don't have the area of a full circle. We only have the area of half of it, the semicircle. So the area of our semicircle, of course, is half of pi r squared. This is simply the area of the semicircle times the thickness, dy, gives us the volume. Now we can replace the radius by its function of y. So what do we get? We get pi over 2. And if I square this, I will square the numerator and denominator separately. So I will have, on the numerator, the square root of 2 minus y minus 2 minus y squared, squaring the numerator over 2 squared, which is of course 4. This is pi r squared over 2 times dy. I'll combine the 2 and the 4 together, and I will not expand this out. I'll leave it as it is for now. So the volume of our infinitesimal semicircle is simply pi over 8 square root of 2 minus y minus 2 minus y, the whole expression squared dy. So now we're getting closer to being done, right? We wanted the volume of the total solid obtained by erecting on the base infinitesimal semicircles that were perpendicular to the base and to the y-axis. But of course, to find the total volume of the solid, we need to sum the volume of every little infinitesimal semicircle over the entire region. So, the total volume will be obtained by summing the volume of every little semicircular cross-section, so pi over 8 root of 2 minus y minus 2 minus y all squared dy. And we're summing with respect to y, and on the base of our solid, the region, the semicircles will begin here when y equals 1, and they'll go all the way up to here when y equals 2. So we must integrate from 1 to 2. And now it's a matter of evaluating this definite integral, and we'll have the volume of our solid. Now here you could be naive, and of course square all of this out. So this squared will give you 2 minus y. This will be easy to integrate, but you'll have twice of this times this, which will be 2 minus y to the 3/2. And on this you'll have to use a U-Substitution. The last term will be 2 minus y squared. If you square this out, you'll be fine. So out of the 3 terms coming out of squaring this expression, 2 can be integrated directly, but the middle term, twice of this times this, will require a U-Substitution. The idea is, if we make the substitution right away, we will save ourselves a lot of work. Before we make the substitution first, let's factor out pi over 8, as it is just a constant multiple. So there it is. Hopefully now you can see what should be our choice of substitution. The idea is to replace 2 minus y by u, by a different variable. I'm going to use u. You could use any other variable. I'm almost out of space, so let me just recopy this on a new page. And you'll see that once we make our u substitution, the integral will become essentially trivial. So our volume was pi over 8, the integral from 1 to 2 of the square root of 2 minus y minus all of 2 minus y, the whole expression squared, dy. And as we've just said, we will let u be 2 minus y. If u equals 2 minus y, the differential of u, du, will be the differential of 2 minus y. The differential of 2 minus y, of course, is the derivative of the function with respect to y, which is -1, times dy as we have a function of y. So du is negative dy. We'll want to solve for dy. Therefore, dy is simply negative du. Okay. Now we need to change our bounds of integration. Let's recopy first what we have. The square root of 2 minus y, that's the root of u, minus 2 minus y minus u, squared, and dy is negative du. So I'll pull up the negative up front, and I'll just put du there. Negative du is the dy. And here again you have to be careful. The bounds of integration will change. Those bounds are for y equals 1, y equals 2, but now we integrate with respect to u, so it must be u equals something, u equals something. Well, 1y is 1, u is 2 minus 1, which is 1. But when y is 2, u is 2 minus 2, which is 0. And now we're good to go. We have replaced everything in terms of y to everything in terms of u. One thing I'll do here, well, two things actually. I'll use a negative here to flip the bounds of integration. If you remember properties of the definite integral, if you interchange the bounds of integration, so if you integrate instead of 0 to 1, instead of 1 to 0, from 0 to 1, so you change the order of the bounds of integration, this negates the integral. But if you negate negative pi over 8, you get positive pi over 8. So first step in simplifying a little bit the expression. And the only way to integrate this will be by squaring it. So root of u times itself is u, minus root of u times u. Twice of that, so minus 2 root of u times u, plus of course u squared. And the only thing missing here is how do we handle this term? But if you think of it, root of u times u, root of u is u to the 1/2 times u, which is u to the 1. When you multiply the same base, you add the exponents. 1 plus a half is 3/2. And now we'll be able to use the power rule on every single term. And the integration is now trivial. So pi over 8. We now find our antiderivative, power rule, u squared over 2. Minus 2 power rule. Add 1 to 3/2, you get 5/2. Divide by 5/2, which means we multiply by the reciprocal 2 over 5. Plus power rule, u cubed over 3. From 0 to 1. And as we are going from 0 to 1, the calculation will be trivial. So we have pi over 8. Antiderivative at 1, so 1 over 2. 1 to any power is 1, so minus 4 over 5. Plus 1/3. So here's our antiderivative at u equals 1, minus, of course, the antiderivative at u equals 0, but 0 to any positive power is 0, so the antiderivative at 0 is 0, so we subtract nothing. So there is the final answer. Of course, we'll just simplify now. So pi over 8. We will put every fraction over a common denominator, which here will be 30. So 15 over 15, so 15 over 30, minus 24 over 30, 6 over 6, plus 10 over 10. So what are we left with? Pi over 8. 15 plus, times 10 over 10, but 3 times 10 is 30, not 10. And now we're good to go. 15 plus 10 is 25, minus 24 is of course simply 1 over 30. So we're in the end, we're left with pi times 1 pi over 3 times 4, 3 times 8 is 24, times 10 is 240. So the volume of our solid is pi over 240 units cubed. And that's it. So if you go back and look at how this fits in with the picture that we had, in the xy plane, a region is bounded by the curves y equals negative x plus 2 and y equals negative x squared plus 2. Here's the region. If we erect on top of this region semicircles that are 1 perpendicular to the region, so again the base of your semicircle will be positioned onto this rectangle in a perpendicular fashion, also perpendicular to the y-axis. So if you position for every little slice of the region these infinitesimal semicircles, this generates a solid, and we found that the total volume of our solid was pi over 240 units cubed. And that's it.